Welcome to the third part of our tutorial, Trigonometry Demystified. Previously, we saw how we could determine the values of the trigonometric functions for some particular values of the angle. In this part, we are going to see how we can calculate those trigonometric functions to arbitrary precision for any angle. And we are going to define three additional trigonometric functions. As a reminder, we saw that the sine, cosine, and tangent of a given angle can be conveniently represented by using the unit circle, and that an angle varying from 0 to 360 degrees corresponds to a full counterclockwise revolution. Instead of defining the angle as varying from 0 to 360 degrees, it is often convenient to define it as varying from minus 180 to plus 180 degrees. This still corresponds to a full counterclockwise revolution. Using this convention, we can now easily analyze the parity of the trigonometric functions by considering 2 points on the circle that corresponds to two angles with opposite values. The symmetry of the figure reveals that the two opposite angles have the same cosine while they have opposite sines and tangents. It follows that sine and tangent are odd functions while cosine is an even function. Let us derive the so-called trigonometric addition formulas, which are very important and useful. Suppose that we know the values of the sine, cosine, and tangent for two angles alpha and beta. We want to know what the values of these functions are for the sum alpha plus beta. Since we know the functions for alpha, it is a good idea to draw a right triangle that has an angle alpha. And since we know these functions for beta, it is also a good idea to draw a right triangle that has an angle beta. But we want to add the angles, so the second triangle should be adjacent to the first one for us to be able to see the sum of the two angles. In order to make the connection with the trigonometric functions of alpha plus beta, we must have a right triangle with that angle. One way to do this is to draw a line from point D that is perpendicular to AB. Now the problem with the new triangle ADE is that it is hard to see how it is related to the triangles for alpha or beta. So what we can do here is to draw a line from C that is perpendicular to DE. This forms a new right triangle CDF. But what is the new angle? Since DF is perpendicular to AB and CD is perpendicular to AC, we can conclude that the angle CDF must be the same as the angle CAB. The angle CDF is just the angle CAB rotated by 90 degrees. Therefore, the two triangles ABC and DCF are similar and the new angle is equal to alpha. Alright, let us write the definition of the sign of alpha plus beta. It is opposite over hypotenuse, DE over AD. From our construction, DE is equal to EF plus DF. Note that EF is the same as BC. Since sine alpha is BC over AC, we can rewrite this as BC equals sine alpha times AC. In a similar way, cosine alpha is DF over CD. Thus, DF equals cosine alpha times CD. If we substitute the expressions for BC and DF in the equation above, we get this new expression. Now, what is the ratio AC over AD? By definition, it is the cosine of beta, and CD over AD is the sine of beta. We conclude that sine alpha plus beta is equal to sine alpha cosine beta plus cosine alpha sine beta. We can now easily determine the sign of the difference alpha minus beta by using the fact that sine is an odd function and cosine is an even function. All we have to do is to replace beta by minus beta in the formula for the sum. It follows that sine alpha minus beta is equal to sine alpha cosine beta minus cosine alpha sine beta. What about the cosine of the sum? By definition, the cosine of alpha plus beta is the ratio AE over AD. But AE can be replaced by AB minus BE. Also, by construction, BE is the same as CF. Cosine alpha is AB over AC, so AB equals cosine alpha times AC. Likewise, sine alpha is CF over CD, so CF equals sine alpha times CD. If we substitute these values in the equation above, we obtain this expression. We can now recognize the ratio AC over AD as cosine beta and the ratio CD over AD as sine beta. Therefore, cosine alpha plus beta equals cosine alpha cosine beta minus sine alpha sine beta. As before, we can easily obtain the formula for the difference by replacing beta by minus beta. As a result, cosine alpha minus beta equals cosine alpha cosine beta plus sine alpha sine beta. For the tangent, we don't need the figure anymore. We can simply write it as the ratio sine over cosine and use the two formulas for the sum that we just derived. We could leave the result like this, but here we can do better and express the tangent of the sum exclusively in terms of the tangent of alpha and beta. All we have to do is to divide both the numerator and the denominator by cosine alpha cosine beta. Let us first divide by cosine alpha. Then sine alpha becomes tangent alpha and cosine alpha becomes 1. Now, if we divide by cosine beta, sine beta becomes tangent beta and cosine beta becomes 1. Cleaning up the result, we get tangent alpha plus beta equals tangent alpha plus tangent beta divided by 1 minus tangent alpha times tangent beta. As before, we obtain the tangent of alpha minus beta by replacing beta by minus beta. As a direct application example, we can use the addition formula to determine the sine of 75 degrees. In part 2 of our tutorial, we determined the values of the sine and cosine for an angle of 30 degrees and for an angle of 45 degrees. So all we have to do is to write 75 as the sum of 30 and 45. I'll let you work it out, and you should find that the sine of 75 degrees is equal to 1 plus root of 3 divided by 2 root of 2. In a similar way, you can find the sine of 15 degrees by writing 15 as 45 minus 30. For us to be able to determine the trigonometric functions for any angle, we need another formula. Let us start from the cosine of a sum. If we substitute beta equals alpha, we obtain a formula for the double angle. The result is easily expressed exclusively in terms of cosines by replacing sine square by 1 minus cosine square. So we obtain cosine 2 alpha equals 2 cosine square alpha minus 1. We can now invert the equation by adding 1 to both sides of the equation, dividing by 2 and taking the square root. We obtain an equation for the half angle. Cosine alpha equals square root of 1 plus cosine 2 alpha divided by 2. This equation can be used to determine the values of the trigonometric functions to arbitrary precision for any angle. Arbitrary precision means that we can give a result as precise as we want. We only have to work more if we want to increase the precision. Let us explain this by looking at an example. Suppose we want to calculate the sine, cosine, and tangent of an angle of 41.26 degrees with a precision of 2 or 3 figures. We can start by choosing an angle that is smaller than 41.26 degrees, but whose double is greater, and for which we already know the cosine. In our case, 30 degrees will work. It is smaller than 41.26 degrees, but the double, 60 degrees, is greater. And we already know the value of the cosine of 30 degrees. We saw that it was root of 3 divided by 2. By successively applying the half-angle formula, we can calculate the cosine of 30 degrees divided by any power of 2. Now we can express 41.26 degrees as the sum of angles for which we are able to calculate the cosine. As a first approximation, we could say that 41.26 is more or less equal to 30. That's not a very good approximation. To improve it, we can try to add 1/2 of 30 to it. That would give 45, which is too big. So instead of adding 1/2 of 30, let us add 1/4. 30 plus 30 over 4 is 37.5. It is still not very good, so let us add to it 30 over 8. Now we get 41.25, which is very close to 41.26. We could keep improving the approximation by adding more terms, but let us work with what we have. We need to know the cosine of 7.5 degrees, but before we need to calculate the cosine of 15 degrees. By plugging the value of cosine 30 degrees into the half-angle formula, we obtain the cosine of 15 degrees. Knowing the cosine of 15 degrees, we can calculate the sine of 15 degrees. Remember, cosine square plus sine square is 1, so sine is square root of 1 minus cosine square. And now we apply again the half-angle formula to obtain the cosine and sine of 7.5 degrees, and one more time to obtain the cosine and sine of 3.75 degrees. Now we can calculate the cosine and sine of 37.5 degrees by plugging the values for 30 degrees and 7.5 degrees into the addition formulas. And then we can iterate and plug the values for 37.5 degrees and 3.75 degrees into the addition formulas to obtain the results for 41.25 degrees. Finally, we make the approximation that the sine and cosine of 41.26 degrees should be close to the sine and cosine of 41.25 degrees. And the tangent is obtained just by calculating the ratio sine over cosine. With this method, the trigonometric functions for any angle can be calculated to arbitrary precision. Before concluding this part, let us define 3 additional trigonometric functions. Note that these functions are not needed, as they contain exactly the same information than the sine, cosine, and tangent. We could even work exclusively with the sine, or the cosine, or the tangent, since they all can be calculated from one another. But having a set of different functions helps us to work depending on the specific problem. Remember that sine, cosine, and tangent were defined based on the observation that the ratio between any two sides of a right triangle depends only on the angle alpha. Since a right triangle has 3 sides, there actually exist 6 possible ratios. The 3 new ratios are called secant, cosecant, and cotangent. The secant is defined as the ratio hypotenuse over adjacent. The cosecant is the ratio hypotenuse over opposite, and the cotangent is the ratio adjacent over opposite. From these definitions, it follows that the secant is just the inverse of the cosine, the cosecant is the inverse of the sine, and the cotangent is the inverse of the tangent. You may wonder where all these names come from. The roots of trigonometry took place with ancient Greek and Hellenistic mathematicians. In these early times, the analysis of angles was made with the use of the chord instead of the sine, cosine, and tangent. Using the chord to analyze angles is totally equivalent to modern trigonometry because the length of the chord is closely related to the sine of the corresponding angle. I'll let you work on it, but it can be shown that the length of the chord in red is equal to 2 times the radius r times the sine of alpha divided by 2. To show it, start by dividing the triangle into 2 right triangles, and you should be able to easily find a relationship between the chord's length and the cosine of alpha. This relationship simplifies to the one that is shown once you make the connection between the cosine of alpha and the sine of alpha over 2. You have to work a little bit on it. But the point is that the entire trigonometry that we know today is totally equivalent to the analysis of the chord. Now the name sine comes from Latin sinus, which means bosom. Yeah, that's totally unrelated. And this is due to early translators who misspelled the word for chord. So sine actually means bosom, but it was supposed to mean chord. In other words, the name sine is just a mistake of history, and there is nothing we can do about it. On the other hand, relative to this mistake, the name cosine is perfectly well justified. To see why, let us go back to our unit circle. By definition, the complementary angle beta is equal to 90 degrees minus alpha. If you apply the addition formula, actually the subtraction formula, to calculate the sine of beta, you will find that it simplifies to cosine alpha if you remember that the sine of 90 degrees is 1 and the cosine of 90 degrees is 0. This means that the cosine of alpha is equal to the sine of the complementary angle, and that's precisely where the name cosine comes from. It is the contraction of complementary sine. For the tangent, you probably already guessed it the first time we made a graphical representation of it. The tangent is called tangent because it lies on the line that is tangent to the circle. And now, I'm sure that you can guess where the name cotangent comes from. The cotangent is equal to the tangent of the complementary angle, and the name is just the contraction of complementary tangent. What about the secant? Generally speaking, a secant is a line that cuts another line or a curve. The secant line that contains the hypotenuse and cuts the tangent line has a length measured from the origin to the tangent point that is precisely equal to the hypotenuse divided by the adjacent side. I'll leave the proof of this to you as an exercise. All you have to do is to consider the 2 similar triangles that clearly appear on the figure, and remember that by definition, the secant is the inverse of the cosine. Finally, you probably guessed this one too. The name cosecant is just the contraction of complementary secant. Remember, the cosecant by definition is the inverse of the sine, and I leave it to you as an exercise to show that it is equal to the distance from the origin to the cotangent point. To conclude this part, We saw how the sine, cosine, and tangent of any angle can be calculated to arbitrary precision, and we defined 3 additional trigonometric functions. In the next part, we will see how the trigonometric functions can actually be calculated exactly for any angle whose value measured in degrees is an integer.